Imagine a cosmic bowling alley, where balls of rock and metal drift through the vastness of space. Welcome to the fascinating world of asteroids. These enigmatic objects have captivated the imaginations of scientists and the public alike for centuries, sparking curiosity and wonder about their origins, compositions, and roles in our solar system. Today, we're diving deep into this intriguing realm. Asteroids are not merely space debris, they are remnants of the solar system's formation, each with its own unique story to tell. As we explore their mysteries, we will uncover how these ancient travelers can provide insights into the very beginnings of our planet and the life it harbors. What if I told you that right now, millions of asteroids are orbiting our sun? Some of these celestial wanderers may hold the keys to understanding the origin of life on Earth, while others could pose a threat to our very existence. Get ready to embark on an exciting journey through the asteroid belt and beyond. As we delve into the wonders of asteroids, don't forget to hit that like button if you're enjoying the ride, and subscribe to our channel, Exploring the Universe, for more cosmic adventures. Asteroids are rocky bodies that orbit the sun, smaller than planets but larger than meteoroids. They are remnants from the early formation of the solar system, primarily composed of rock and metal. Unlike planets, asteroids do not have atmospheres and are irregularly shaped, often resembling giant, misshapen boulders. Asteroids vary greatly in size, from small rocks measuring just a few meters across to massive bodies hundreds of kilometers in diameter. For example, Ceres, the largest known asteroid, has a diameter of about 940 kilometers, about 584 miles, while many others are just a few meters wide. This diversity in size plays a significant role in their formation and the processes that created them. While asteroids, meteors, and comets are all celestial objects, they have distinct differences. Asteroids. As mentioned, these are rocky bodies that orbit the sun, primarily found in the asteroid belt between Mars and Jupiter. They are considered the building blocks of planets. Meteors. When a small fragment of an asteroid or a comet enters Earth's atmosphere and burns up due to friction, it creates a streak of light known as a meteor. If it survives its passage through the atmosphere and lands on Earth, it is then called a meteorite. Comets. Comets are icy bodies that originate from the outer solar system. When they approach the sun, they develop a glowing coma and a tail due to the sublimation of their ice, which differs significantly from the solid and rocky nature of asteroids. The history of asteroid discovery began with Ceres, identified by Italian astronomer Giuseppe Piazzi in 1801. Initially classified as a planet, Ceres was later reclassified as an asteroid and eventually designated as a dwarf planet due to its size and spherical shape. Its discovery marked a pivotal moment in astronomy, highlighting the existence of other celestial bodies within our solar system. The discovery of Ceres led to the hypothesis that there could be a lost planet, situated between Mars and Jupiter. Early astronomers speculated that this region, now known as the asteroid belt, was once home to a planet that may have been destroyed or never fully formed. This idea spurred interest in the study of asteroids and their potential to reveal the secrets of planetary formation. As technology advanced, so did our ability to discover and study asteroids. The invention of powerful telescopes allowed astronomers to identify and catalog thousands of asteroids. The advent of space missions further revolutionized our understanding. For example, missions like Near Shoemaker, Dawn, and OSIRIS-RX have provided invaluable data on the composition, structure, and history of various asteroids, transforming them from abstract concepts into tangible objects of study. With each discovery, we gain deeper insights into the origins of our solar system and the processes that govern it, revealing the significant role asteroids play in understanding both our cosmic history and our future. Asteroids can be categorized into three primary types based on their composition. C-type. These are the most common asteroids, making up about 75% of known asteroids. C-type asteroids are rich in carbon and often contain clay and other minerals. They are typically dark in appearance and are believed to be some of the oldest objects in the solar system, preserving the primordial materials from which the planets formed. Their study is crucial for understanding the early solar system. S-type. Comprising approximately 17% of known asteroids, S-type asteroids are primarily made up of silicate minerals and nickel iron. They are relatively brighter than C-type asteroids and are often found in the inner asteroid belt. The presence of metallic elements suggests that these asteroids may have formed from the remnants of larger bodies that underwent differentiation, giving us insights into the processes that led to the formation of terrestrial planets. M-type. These asteroids are primarily composed of metallic elements, predominantly nickel and iron. M-type asteroids represent a smaller fraction of the population, but are of great interest due to their potential for containing valuable resources. Their metallic nature indicates that they may be the remains of the cores of differentiated bodies that were broken apart during collisions. Understanding the composition of asteroids is vital for several reasons. First, it sheds light on the conditions and processes that prevailed in the early solar system. By studying the materials found in asteroids, scientists can infer the temperature, pressure, and chemical environments present during their formation. This information helps us piece together the history of our solar system and the evolution of planetary bodies. Additionally, the composition of asteroids has practical implications for future exploration and potential resource utilization. For example, the presence of water ice or metals could support future mining operations or serve as resources for long-duration space missions. The main asteroid belt is located between the orbits of Mars and Jupiter and is home to the majority of the solar system's asteroids. This region is characterized by a vast array of asteroids, ranging in size from tiny boulders to large bodies like Ceres. Estimates suggest that there are millions of asteroids in this belt, though only a fraction has been catalogued. The gravitational influence of Jupiter is believed to have played a significant role in shaping the belt structure, preventing the formation of a larger planet in this region. Trojan asteroids are found at the Lagrange points of Jupiter, specifically at the 60-degree leading and trailing positions relative to the planet in its orbit. These asteroids share Jupiter's orbit around the Sun and are considered stable due to the gravitational balance at these points. The study of Trojan asteroids provides valuable insights into the early solar system, as they are thought to have originated from the same region as the gas giants. Near-Earth asteroids are those that have orbits that bring them close to Earth. These asteroids are of particular interest due to their potential impact risk and the opportunities they present for exploration. Scientists actively monitor NEAs to assess potential threats to our planet and to study their compositions and structures. Understanding NEAs is crucial for developing strategies for planetary defense, as well as for utilizing their resources for future space missions. Isn't it incredible how our solar system is filled with surprises? If you're enjoying this journey through the world of asteroids, show your enthusiasm with a like. And don't forget to subscribe for more fascinating cosmic adventures. Asteroids are considered the leftover building blocks from the formation of the solar system approximately 4.6 billion years ago. When the solar system was in its infancy, a vast disk of gas and dust surrounded the young sun. Through a process called accretion, particles collided and stuck together, gradually forming larger bodies. While many of these bodies eventually coalesced to form the planets, some remained as smaller, rocky entities, what we now refer to as asteroids. These remnants provide a unique glimpse into the conditions of the early solar system, offering clues about the materials and processes that were present during the formation of the terrestrial planets. Throughout their history, asteroids have been subject to numerous collisions with one another and with other celestial bodies. These impacts can lead to fragmentation, creating smaller asteroids or even meteoroids. The aftermath of such collisions can significantly alter the orbits and compositions of the resulting fragments. In some cases, these collisions can result in the formation of asteroid families, groups of asteroids that share similar orbital characteristics and likely originated from the same parent body. The Yarkovsky effect is a phenomenon that affects the orbits of asteroids due to the way they absorb and re-radiate solar energy. As an asteroid rotates, it absorbs sunlight and heats up, then re-emits that energy as infrared radiation. If the asteroid is not perfectly spherical, this process can create a small thrust that alters its orbit over time. This effect, combined with gravitational interactions with larger bodies like planets, can lead to the migration of asteroids from their initial positions, potentially bringing them closer to Earth or into the asteroid belt. Ceres is the largest known asteroid in the solar system, with a diameter of about 940 kilometers, about 584 miles. Initially discovered in 1801, Ceres was reclassified as a dwarf planet due to its size and spherical shape. It resides in the asteroid belt and is notable for its water ice and potential for hosting organic molecules. Ceres offers insights into the conditions of the early solar system and the processes that shaped planetary bodies. Vesta is the second largest asteroid, measuring about 525 kilometers, around 326 miles, in diameter. Unlike Ceres, Vesta has a differentiated internal structure, indicating that it underwent processes similar to those of larger planets. It has a unique surface with large craters, and its study provides vital information about the thermal history of asteroids and the conditions that led to planet formation. Psyche is a unique asteroid with a diameter of approximately 226 kilometers, about 140 miles, and is thought to be the exposed metallic core of a protoplanet that never fully formed. Located in the asteroid belt, Psyche presents an opportunity to study the building blocks of planet formation and offers valuable insights into the nature of metallic bodies in the solar system. A mission to Psyche is currently planned to further investigate its properties. Both Bennu and Ryugu are significant due to their recent exploration by space missions aimed at sample return. Bennu, a near-Earth asteroid, was visited by NASA's OSIRIS-RX mission, which collected samples in 2020. Ryugu, visited by Japan's Hayabusa 2 mission, also returned samples in 2020. These missions have provided invaluable data on the composition and structure of asteroids, enhancing our understanding of the solar system's history and the potential for resource utilization in space. Asteroids are considered time capsules from the early solar system. Many of them have remained relatively unchanged since their formation, preserving the original materials and conditions that existed billions of years ago. By studying the composition of these bodies, scientists can gain insights into the solar nebula, the cloud of gas and dust from which the solar system formed. This primitive composition helps us understand the building blocks of planets and the materials available during the early stages of planetary formation. The study of asteroids provides vital clues about the processes that led to the formation of planets. For example, the differences in composition and structure among various types of asteroids reveal how temperature, pressure, and distance from the Sun influence the materials that coalesced into larger bodies. By examining asteroids, scientists can piece together the timeline of solar system evolution, offering a clearer picture of how planets like Earth came to be. Asteroids are increasingly seen as potential sources of valuable resources. Many of them are rich in rare and precious metals, such as platinum, gold, and other elements that are scarce on Earth. The feasibility of mining asteroids presents exciting opportunities for future space exploration and resource utilization. Space mining could provide materials for construction and fuel for long-duration space missions, reducing our dependence on Earth resources and enabling further exploration of the solar system. Asteroids also serve as natural laboratories for studying the physics of space. Their unique environments allow scientists to investigate phenomena such as microgravity, radiation exposure, and the effects of solar wind. By conducting experiments on or in proximity to asteroids, researchers can gain insights into fundamental physical processes that are difficult to replicate on Earth. This knowledge is crucial for understanding not only asteroids but also the broader dynamics of celestial mechanics and planetary science. Tunguska Event, 1908. One of the most significant asteroid-related events in history was the Tunguska Event, which occurred in Siberia. A large explosion, believed to be caused by the airburst of a small asteroid or comet, flattened an estimated 2,000 square kilometers of forest. This incident highlighted the potential dangers posed by near-Earth objects and underscored the need for monitoring and understanding these celestial bodies. Another notable event occurred in 2013 when a meteor exploded over Chelyabinsk, Russia, causing extensive damage and injuries. The Chelyabinsk meteor, which was about 20 meters in diameter, entered the atmosphere at a high speed and released energy equivalent to approximately 470 kilotons of TNT. This incident reinforced the importance of tracking NEOs and understanding their potential impact risks. To mitigate the risks associated with NEOs, various programs and initiatives have been established for monitoring and tracking these objects. Organizations like NASA and ESA have developed systems to identify and catalog NEOs, assessing their orbits and potential threats. Continuous observation helps scientists predict the paths of these objects and determine if they pose a risk to Earth. In response to the potential threat of asteroid impacts, scientists and engineers are developing strategies for planetary defense. One of the primary concepts is asteroid deflection, which involves altering the trajectory of a threatening asteroid so that it no longer poses a risk to Earth. This could be achieved through various methods, such as kinetic impactors that collide with the asteroid to change its course or gravity tractors that use gravitational pull to gently nudge the asteroid over time. These efforts underscore the importance of understanding asteroids not just as scientific objects of study, but also as potential threats that require proactive measures to ensure the safety of our planet. By advancing our knowledge of asteroids, we not only learn about the history of our solar system but also develop the tools necessary to protect Earth from potential impacts. The Near-Shoemaker mission, launched by NASA in 1996, marked a historic milestone in space exploration as it became the first spacecraft to land on an asteroid. In 2001, Near-Shoemaker successfully touched down on Eros, a near-Earth asteroid measuring about 33 kilometers, 20 miles, in length. The mission provided invaluable data about the asteroid's surface, composition, and geology. Using its instruments, Near-Shoemaker gathered high-resolution images and spectroscopic data, revealing details about Eros's irregular shape, craters, and surface materials. This pioneering mission paved the way for future asteroid exploration and demonstrated the feasibility of landing on such small celestial bodies. The Dawn mission, which launched in 2007, aimed to study two of the largest bodies in the asteroid belt, Vesta and Ceres. Dawn was equipped with advanced instruments to analyze the surface composition, geology, and internal structure of these celestial bodies. At Vesta, Dawn orbited the asteroid from 2011 to 2012, capturing detailed images and data that revealed Vesta's differentiated interior and complex geological history, including evidence of past volcanic activity. After leaving Vesta, Dawn traveled to Ceres, entering orbit in 2015. The spacecraft discovered bright spots on Ceres, which were later identified as deposits of sodium carbonate, indicating past hydrothermal activity. Dawn's findings provided critical insights into the evolution of both Vesta and Ceres, contributing to our understanding of the early solar system. OSIRIS-Rx, launched in 2016, targeted the near-Earth asteroid Bennu. In October 2020, the spacecraft successfully collected samples from Bennu's surface, which are expected to return to Earth in 2023. This mission aims to analyze the samples to understand the building blocks of life and the conditions in the early solar system. Hayabusa 2, launched by the Japan Aerospace Exploration Agency in 2014, visited the asteroid Ryugu. In 2019, it collected samples and returned them to Earth in December 2020. Like OSIRIS-Rx, Hayabusa 2's mission focused on understanding the composition of carbon-rich asteroids and their role in delivering organic materials to Earth. Looking ahead, several exciting missions are in the pipeline for asteroid exploration. NASA's Psyche mission aims to study the metallic asteroid Psyche, believed to be the exposed core of a protoplanet. Scheduled for launch in 2023, this mission will provide insights into planetary formation and the nature of metallic bodies. Additionally, JAXA is planning the Hayabusa 3 mission, targeting another asteroid for sample return. International collaboration on asteroid missions is also on the rise, with various space agencies discussing joint efforts for future exploration. The future of asteroid research is bright, thanks to rapid advancements in detection and characterization technologies. Improved telescopes, both ground-based and space-based, are enhancing our ability to identify and track asteroids. Techniques such as radar imaging and spectroscopy allow scientists to determine the size, shape, rotation, and composition of asteroids with greater accuracy. Machine learning algorithms are being developed to analyze vast amounts of observational data, enabling more efficient identification of potentially hazardous asteroids. As interest in space resources grows, asteroids are becoming prime targets for mining and commercial exploration. The potential to extract valuable metals, water, and other resources from asteroids could revolutionize space exploration and industry. Companies are exploring the feasibility of asteroid mining, which could provide raw materials for use in space infrastructure or even for use on Earth. This prospect raises questions about the economic viability and regulatory frameworks needed to govern space resource utilization. Asteroids may also serve as stepping stones for future deep space exploration. Their relatively low gravity and proximity to Earth make them ideal candidates for refueling stations or bases for missions to more distant destinations, such as Mars or the outer planets. Utilizing asteroids for staging missions could significantly reduce the costs and risks associated with deep space travel. As we continue to explore and understand asteroids, they will play a crucial role in humanity's journey into the cosmos, unlocking secrets of our solar system while potentially providing the resources needed for further exploration. Asteroids, far from being mere space debris, are scientific treasures that hold the secrets of our cosmic origins. These fascinating objects are remnants of the early solar system, providing insights into the conditions and processes that shaped our planetary neighborhood. By studying asteroids, we unlock the history of our solar system, gaining a better understanding of how planets formed and evolved over billions of years. Moreover, asteroids represent a dual nature. On one hand, they pose potential threats to Earth through impacts, as evidenced by historical events like the Tunguska and Chelyabinsk incidents. On the other hand, they are sources of invaluable resources, containing rare metals and materials that could fuel future space exploration and even support life beyond our planet. This duality makes them captivating subjects for both scientific inquiry and practical application. As we advance in our exploration of space, asteroids will undoubtedly play a crucial role in our journey to unravel the mysteries of the cosmos. They may serve as stepping stones for deeper space missions, resources for interplanetary travel, and keys to understanding our own origins. The study of asteroids continues to challenge our perceptions and expand our horizons, reminding us of the vastness and complexity of the universe. If this journey through the world of asteroids has sparked your cosmic curiosity, don't stop here. Give us a like, share with your friends who are passionate about astronomy, and subscribe to our channel, Exploring the Universe. Together, we will continue to explore the wonders of our solar system and beyond. Until next time, perhaps from the surface of an asteroid.